In this lecture, we are going to explore experimental research, experimental design. This will take us beyond those universal characteristics we've learned about in our previous lectures, beyond those overviews and general quantitative research. And we're going to get to dive deeper into experimental research design and further along the way in our research planning. What comes to mind when we think about experimental research? If we were sitting face-to-face in a lecture, we would break up into some groups and take 15 minutes or so and discuss our thoughts and ideas behind what experiments were, experimental research, experimental design, because although we may not know for sure some of the meaning of experimental design and experimental research, we're not completely unknowledgeable about what research or experiments or about what the word experimental means. But we might have too broad or narrow of a perspective when it comes to experimental design. So a lot of times when we start to think about experimental research, types of things that might come to mind for you might be experimental designs, experimental structures, experimental vehicles, whether it's a car, a truck, or an airplane. Maybe start to think about what the future looks like. What would a future housing look like? What are the future models, which are experimental models? Maybe an experimental model is geothermal use of energy or solar-powered houses. Technology, whether it's artificial intelligence or more concrete examples in the form of future robots or existing technology. And maybe when you think of experimental nowadays, you also think of experimental drug technology, experimental vaccines that are currently out there in the forefront, the leading edge of research. Continue on this idea of a discussion and moving away from just experimental research as a novel approach or procedure, we'll probably start to think of ideas of experiments and what we think of experiments from all of the lived experiences we bring to this classroom. Some of us have had a chemistry class or biology class where we do very refined experiments in a laboratory. Maybe you've had that crazy professor that's done a stage experiment for you all, or maybe even at younger ages, high school, undergraduate, you've got to participate in some of those types of experiments. So maybe as you begin to think about what experimental research is, you might think back to some of the things you've done or witnessed in some of the hard sciences. We often hear about cool experimental research being done in space under laboratory conditions. Sometimes those experiments are adaptations of experiments we could do in a classroom setting. And other times they are the experimental research that starts as mind experiments. And when they are developed, for example, with the double slit experiment here, it can change the entire face of a field of study, like in physics, quantum physics. Experimental research can sometimes be as simple as plants in pots or fungi in a petri dish. So we might be exploring different soil types or different acid and pH levels. It might be very broad. We might be looking in the ocean for renewable resources and how that impacts some of the environment that it will be set within. So our experimental research may be revolving around something as narrow as a greenhouse or as broad as the ocean. If we were sitting around face to face and talking about experimental research or virtually online having this discussion, we'd probably have someone come up with the idea of the lab rat in the maze looking for cheese or maybe some other sugary substance to make it happy and try and learn, understand the process of learning in these rats. You may come up with spooky ideas behind this or loving ideas behind this. I will say I definitely had colleagues doing some experimental research on their lab rats, which sounds a little ominous, except they were doing similar things with sugar water. And when, through the process, they named their rats and took them home as pets after the experiment was complete. But the idea here is what is going on. So, when you think about the classic experimental situation, what is it that we're doing? And I think some of this alludes back to the control in our studies. For myself, I have a background in psychology and education and some other fields as well. I really enjoyed the study of the mind and the study of the brain. I really had a deep interest in the psychological factors of how we learn, how we know what we know, the connection between what folks call the mind brain. In psychology, we certainly have other types of experiments as well. Sometimes we're trying to understand the inner workings of the mind with electrodes, and other times we may present our experiments on laptops and try to understand what is going on in the mind. In this type of research, we tend to see a lot of crossover. We see crossover with neurology. We see crossover in education when it comes to learning. We see crossovers in biology and computer technology. And that's true of so many of our research settings. And finally, we'll come to a setting that might be familiar to us all, being in the classroom. What does educational research look like? We might think of our current situations if we were face-to-face. Perhaps we're in a lecture hall, large lecture hall. Perhaps think of the high school or smaller college classroom sizes, or we may think of open concept learning environments, as well as right now, many of us are learning and participating from either hybrid models or at home. It would probably be rather unexciting research for us if we left those seats empty. We might want to fill up our chairs in an experimental research design, understand what the materials we're working with, who are the subjects we're interested in, what are the goals of our research? Do we have a hypothesis? What about our outcomes that we'd like to measure? Do we have tests that we're going to instill? Are we going to do observations of persons? We would begin to think about how we might deconstruct our research experiments, any of those experiments, whichever one is closest to your field, whether it's psychological experiments or educational settings. We would begin to think about what are the attributes we already know something about, and how might we begin to apply them to these experimental designs that we're going to see today. Hopefully you played along a little bit with me on the thoughtfulness experiment. What is experimental research to you? Today we're going to be a little bit more rigorous as we move into what is experimental design. What are the characteristics of a good design? We'll get more into issues of validity. We're going to revisit some of those issues and threats to validity. We're going to explore specific types of designs, some issues around results, and randomness. What is experimental research? We started off here by thinking about some ideas about experiments. What is experimental research to us? Well, let's give a little bit more formal definition of what we mean by experimental research. Experimental research is a scientific approach to doing research. Under a specified research conditions, at least one independent variable is manipulated. That independent variable is systematically varied with a predetermined methodological plan behind it. Our goal is to determine the cause and effect relationship based on those manipulations. So we can think about this as we want to test something and determine its effect. You can think about that something as some sort of intervention or treatment effect. And critical here is that a variable of interest, the experimental variable, it's an independent variable, but it is manipulated. So when we say experimental variable, that's what we mean. And it's been manipulated or varied by the researcher. One of the examples I use, which mirrors some of the examples from your textbooks, is the idea of having a teaching method. So I always consider myself in the situation where I'm teaching face-to-face courses, online-only courses, and hybrid courses, and I'd like to know something about the effectiveness of those different methodologies. So I might put myself in a situation where maybe I have participants, and I have a face-to-face lecture, a hybrid version of that lecture, and an online-only version of that lecture. Perhaps if I'm so lucky, I could actually randomly assign individuals to different groups and afterward have a relatively short assessment that I might use as my dependent variable. Ideally, that dependent variable is a measure related directly to my lesson plan. So maybe my lesson plan for all three is about an hour total, and I can divide people up into each one of those three groups. Here we would think of the control that I have is the different types of teaching methods, whether it's face-to-face, a hybrid style course, or online. And then I randomly assign people to each one of those sections. And the outcome, what we're actually measuring though, is the dependent variable, is that short assessment. Probably not surprising to any of you that I'm asking for a pause moment here. If you haven't already, go grab your research questions and your hypotheses that you've written down before and play along with us as we go through some experimental designs here. I'll just use one we've used before, so give us another example. That healthy snacks, I think there's an idea here that healthy snacks will have an impact on mathematical ability. I'm going to keep it simple. Often what we find out in experimental design is that we think because it's experimental that we mean complex. And I would say the opposite is true. That when all things being equal, if you can keep your actual design simple, you should do so. It's not often that we actually can uncover what we'd like to uncover and keep it simple. But if we can do that, that's still good quality research. We don't have to get complex for the sake of doing so. So in the spirit of simplicity here, and also just to get us started on experimental research designs, we're going to have a very basic hypothesis, which is just that the use of healthy snacks will increase performance on math assessments. We're looking at middle school children, age 7th graders. And our variable that we're going to manipulate are the healthy snacks, and our dependent variable that we're going to measure is our math ability. Hopefully this looks relatively familiar to you. It's a simplified version of my study before. So previously I was interested in a gender effect, and I also had a third group. For us, just starting off, we can just think about a simple experiment where we offer no snack to group 1 and a snack of apples to group 2. And we're going to test the hypothesis that the use of healthy snacks will increase performance on math assessment among middle school children. I have control over the snack. That is, I can offer apples to one group and nothing to the other. I also could increase my control. I could add more snacks. I could change the snack. If I just have two groups, perhaps I could do chips versus apples. I could make those decisions as the researcher. So I have a lot of control over that experimental variable or manipulated variable. It's our independent variable to which I have control. That is not what we are measuring. I just leave that pause there for a moment, because we often confuse our independent variable and our dependent variable in the sense of what we're actually measuring. We're looking for a difference between healthy snacks in this case and no snacks. But what I'm actually measuring is the dependent variable, the performance on math tests. Perhaps there's no difference that occurs whatsoever, no difference between snacks or apples, or even if I throw in other groups, I found no difference amongst these groups on the performance on a math test. I measured the performance of the math test. My independent variables, what I'm controlling, what I'm manipulating, what I'm using for prediction, but it is not what I'm actually measuring. What I actually am looking at as an outcome, in this case, is the performance of my math on a mathematical assessment. We'll come back to this design, this research hypothesis, and the design underlying it as well as a few others as we go through some of our experimental designs. But I just want you to see that an experimental research condition can be very, very simple, very basic, yet what it could tell us could be very meaningful. Our experimental designs, these are the preconceived plans for conducting an experiment, our strategies for conducting an experiment. We can think of them as structures by which variables are positioned, arranged, or built into the experiment. I have an example of the Colosseum here. The insides of the Colosseum made it a very adaptable arena to many different conditions. The modern day sports arenas, you don't have to be a sports fan here. Just I give different examples, different structures: baseball, football, hockey, basketball. Each one is a structure designed to bring persons, participants, subjects, people into watch an event. That event is a predefined plan. There are specific outcomes we're looking for, variables and conditions. Even if you go to a baseball stadium in one location, there may be differences in the structure of a baseball game in another location. So these are the structures. We can think about them as tangible buildings, but in our world, we're going to build experimental designs that are the structures by which we're structuring our variables and our participants so that we can have control over an experiment. So if sports aren't your thing, you can think about TV shows. You could think about the internet. You could think about websites. The structure by which the show is going to be conducted is built ahead of time. We have Jeopardy here and Brunch with Bobby as an example. Two very different shows. They're both going to have a structure. They're going to contain, finger quote variables, outcomes that we're expecting to see. There's going to be people involved. So we can think about the set of a show partly as an analogy for experimental design here as well. In general, I feel like I can't say it too often about experimental variables, independent variables, manipulated variables. All experimental variables and manipulated variables are our independent variables, although we'll see later on when we get into quasi-experimental and non-experimental designs that not all independent variables are manipulated. So our variables we're interested in, well, we have variables which we're going to manipulate in the experiment, and we're going to have variables that we're going to look at as outcomes. Our previous example, we saw that in our healthy food eating for kids in middle school, we were looking at no healthy snack or no snack at all versus the apple condition, which was the healthy snack. That is what we as experimenters are manipulating, even though the outcome might be some score on a test. The levels that we have, whether we have 2 levels or a lot of levels, many levels, infinite, potentially infinite many levels of variables, those levels are the treatment effect. That is the experimental treatment that we're interested in. In our case, originally, it's apples versus, healthy snacks versus no healthy snacks. We might think about coffee or caffeine as a drug. And we might have experiment where we have control of water, no caffeine. Perhaps we have 1 cup of coffee, but we have it measured out. How much it is and what the dosage of caffeine is. And then we have a larger cup within a safe region. We could have any of those numbers in between, right? We could have 1 milligram, 10 milligrams of caffeine. We could have 1 cup of coffee, 2 cups of coffee, 3 cups of coffee. As long as it's within safe levels for our experiment, we can think of that as our drug. And the dosage itself becomes the treatment, the experimental treatments, the levels of our experimental variable we're interested in. We can think of a lot of different types of experimental variables, perhaps new instruction method or a type of therapy. When I say therapy, even multiple things may come to mind. You might think of classical types of psychiatric therapies or physical therapy or play therapy. So there could be therapy that involves medicine, therapy that involves physical activity, therapy that involves exercise. We would pick one of those types of therapy along the line, and we could determine different levels, different treatments that we are involving as our experimental condition. For all of the examples that we're giving, we have the experimental variable, the type of the drug dosage for an experiment, or a type of instructional method or type of therapy used, the variable, the experimental variable has different levels, the experimental treatments, but what's really important is that the researcher can manipulate or control those levels. If we don't have control, that's going to be a different types of designs we're going to look at later on in the next couple lectures. Our research, especially in the social sciences and education, it just doesn't work without subjects, without participants. Subjects are simply someone who participates in our experiment. Notice the word participates. They are a participant. They receive the treatment or some control. We typically use a symbol S to represent them. When we're writing about subjects, though, often we use the term participants. If they're in education, sometimes you see the word student, if that is appropriate as well. In medicine, sometimes you also see patient besides subject and participant. One of the things to note, and the reason I highlighted the idea of participant, is that it demonstrates subject tends to connotate that they have very limited or no autonomy, whereas a participant is a member of the study itself. And as we read in the Belmont Report and other ethical works we've been reading earlier on, that matters to us in research. It's useful for us, before we get into the specifics of our designs, to talk about what are the criteria for a well-designed experiment. We'll also investigate a little bit more about validity and threats to validity as well before we get into the specifics of the design. So let's talk about the criteria for a well-designed experiment. And as we do, I have the pause button up here, probably not surprising to you, just so you can have your design ideas already in mind or thoughts about your hypothesis and research questions in mind, and start to be thinking about how these issues might impact the intuitive designs that you have in mind already. Our first criteria is adequate experimental control. We want to be able to control the effect of other extraneous variables such that we can interpret the results and attribute the effect to the experimental variable. We also want to make sure to have enough control so that if the experimental variable should have an effect, that we can detect it. Well, in some situations, enough control could mean a lot of controlling extraneous variables and building in variables into a model. For example, if you were dealing with the International Space Station and an experiment, there may be a lot of design elements into an experiment that would need to take place. But other times, very simple. The control that we need are just some sort of partitioning, some way of separating out our treatment and control groups from each other. Could be our example from previous with our healthy snacks, that we have just classrooms split up, maybe two different rooms, and one room gets the apple and the other room gets nothing. In the case of our experiment in the classroom, where we have two different groups, we randomly assigned 30 different students to each of those categories, to each of the treatment levels. Treatment level 1 being the control, no snack, and treatment level 2 being the apple that they get in that classroom setting. The idea being that we're controlling all other variables through the idea of randomization. But if we wanted to, we could also make attempts to build other independent variables into the model if we thought we couldn't control those variables. Our next criteria for a well-designed experiment is lack of artificiality. We'd like to design our experiments in such a way, typically, that we'd like generalizability. We want to be able to generalize from the experiment to non-experimental conditions. For example, if we have our healthy food eating a healthy snack, we want to be able to generalize it back to real classrooms. Now, the classroom itself, one might argue, is an artificial environment, but it's an artificial environment that we're in on a regular basis and throughout a K through 12 education. But they look differently depending on what type of classroom and what age the students are, the kids are in your classroom. So always think, if you plan to generalize it back to the real world, is your experiment set up in a way that's artificial, or are there real applications to the experiment you designed? And we'll note that throughout the example I've been giving, there's been a comparison group. A well-designed experiment should have some sort of comparison group. We want to be able to make a comparison to determine whether or not there was an effect due to the experimental variable, due to our treatment versus a control, or even in some experiments, it's treatment compared to other treatments. Note here my little sad face versus an apple is simply my impression that if I was in the experimental condition where the group got no snack and I found out the other group got a snack, I might be a little sad. Now that seems, fun and silly in some ways, but one should think about this. Like, if you're in the control group, what is a real control? If that were known that one group was getting a snack and one group wasn't, you might want to balance this in a different way. There's also the very act of eating may be some sort of confound in the experiment. So perhaps the idea I had before with chips or something, there needs to be another treatment effect to compare this to. I say this because as we're just getting to 3 different criteria for controls, there is a lot of balancing that goes back and forth, and I'll talk more about that in a moment. But whether it's adequate experimental control, lack of artificiality, or a comparison group, we balance these things out. It's not necessarily perfect. That is, we're not going to have perfect generalizability back to the real world in an experiment, but we'd like there to be some. So we consider, how could that be the case? And we want to have comparison groups, but we probably could not afford to have 20 different comparison groups in a design such as this. So we simply balance out those types of criteria for our design. Next, we look at adequate information from the data. This is adequate information to test our hypothesis. We can think about the size of the classroom we might be dealing with. So the data that we have, if we're in an experimental setting and I'm collecting information for my healthy eating hypothesis, I want to make sure I have enough data that my statistical method that I'm going to be used will be precise. That's a technical term. That is, we're going to be concerned about having enough precision to be able to detect and make a decision in my hypothesis. Another issue that goes along with this for adequate data is a balance of the data. For example, if I have 3 students in the no snack group and 100 students in the group that gets the apple, there could be a balancing issue with the statistic that I use to get statistical precision to test my hypothesis. And we'll learn more about this when we get into hypothesis testing. We also want to consider issues of contamination in our data, uncontaminated data. So our data should be free of measurement error or mistakes that might be made in procedures. One thing we might think here is we don't want our 2 groups to interact. So you don't want the groups telling each other what's going on, if possible. I mean, there's always threats to validity we'll discuss in a moment. But if the group 1, prior to taking the test especially, imagine that group 1 finds out they had apples and the other one found out the other group didn't. There may be another effect that goes on. Another type of contamination could be, here I just make you think about how far away would you have to go before you would drink this water. Well, a couple reasons I mention this from a contaminated perspective. One is, things can impact our experiment we just don't expect. Imagine in both classrooms, if right before we came in to do our experiment, we had snack time prior to that with every single student in the classroom, in both classrooms, had a snack, whatever it is that they chose to have, or whatever it is, if they were 7th graders, someone packed it for them. That would really contaminate our results. And the other reason I say this is because sometimes it's impossible, it's difficult or impossible to decontaminate something, that you would be far enough away from the source of contamination that you might be able to clean that, or say the data is free from measurement error. So a little bit of prevention up front is really worthwhile here. There's no perfect scenario. We're balancing out these criteria for a well-designed experiment. Now, we also don't want confounding, so we want no confounding of relevant variables, which means this ties back to our adequate experimental control. Any other variables that might impact our study that we can't control through randomization, we need to make an attempt to separate or control those variables in our research design. So for example, what if someone says to me, after I come up with my hypothesis, I find an effect, right? The control group no snack versus the healthy snack, and I find an effect. Someone says, it's not due to healthy snack, it's just due to a snack. If you had eaten chocolate bars of the same number of calories, you would have had the same impact on your outcome. Well, there's the possibility that that is a relevant variable, that calorie intake is a relevant variable, and I may need to extend it back to that third group, whether I have chips or a sugary snack or something that's more neutral as a snack. We may want to have it something that we don't consider as a healthy snack to be able to determine whether it's eating versus not eating. And then if it is eating versus not eating, then is there still a difference between healthy snacks and what we might consider unhealthy snacks? So anyway, I want to say that there's a link back to experimental control, but think about this also specifically about issues that might confound your experiment or the results of the statement you want to make about your hypothesis. Our representativeness ties back into lack of artificiality. We want to make sure that we're able to generalize our experiments, and in doing so, we want to be able to have a representative sample from the population that we're interested in. In doing so, we would have some sort of one of the best ways to do so is a random selection process of subjects into your sample from the population that you're interested in. The mechanisms for this, there's a lot of different ways of conducting random selection, whether it's through picking names out of a hat with or without replacement, one would specify, we'll talk more about that later, or whether it's virtual and through Excel or some generator that you may have for random selection, or process that you have. One of the strongest mechanisms to be able to generalize back to the population from your sample is through random selection. Parsimony is keeping things simple. With all other characteristics being equal, a simpler design is preferred. We often think the opposite, that a more complex one will create a better experiment, but that is not true. If all things being equal, or relatively equal, as we'll find out in some of our quasi-experimental designs, that we want to keep our designs simple. Of course, there are situations where the complexity of the design, like the same design in a classroom setting versus the same design on the International Space Station, would have different levels of complexity, but what is simple for each of those settings is important. Finally, I'll say with these criteria, there's some art to making of our science. So this means that we want to balance these criteria. Every experiment may call for a different sort of control and different types of criteria that we need to focus on. Our parsimony, keeping things simple, helps us with interpretation, but in another scenario, we may be more concerned with lack of artificiality or contamination of our data. So in each scenario as they arise, our experimental designs, we should be requiring, taking our attention toward all of these criteria, but balancing them. You'll never have an experiment where you have perfect generalizability and perfect control within your experimental design. But the idea is that you balance out many of these criteria that are for a well-designed experiment, so that as you go through, you believe the findings that you have, you maintain safety of the experiment, and you'll be able to support and interpret the findings for the hypothesis and questions that you're asking. You also can view our well-designed experiments as enhancing experimental validity. So we are back to the validity of our experiment, experimental validity. Internal validity is really the focus of cause and effect. We want to be able to believe the extent to which our results of our research can be interpreted accurately, and to this extent with no plausible alternative explanation. The stronger our internal validity, the more likely we believe the cause and effect relationship between the independent and dependent variable. What we want to believe is that the changes that occurred in the dependent variable are due to the manipulations of the independent variable. The stronger our internal validity, the more plausible we believe the outcome of our results. This is directly balanced by the idea of external validity. We want to know the extent to which our results are generalizable. That means generalizable from the sample, from the situation, from the conditions we've put in our internal validity, our experiment, from the sample that we're looking at or observing, or a classroom that we're watching, to the general population and situations and conditions that could occur. One might say that the more extensive the results of our, given external validity, the more extensive the results, the more useful the interpretations, but it's conditional first on internal validity. If you don't have internal validity, if you don't believe the cause and effect relationship, if you don't have a rationale to interpret that your independent variable has some impact on your dependent variable, then it doesn't matter about your generalizability, because the internal validity, the results, you're not necessarily interpreting accurately. We also might note that, things like weak external validity, only allow for a very narrow interpretation. So even if you have strong internal validity, but then you have very, very weak external validity, then you're only going to be able to interpret the results toward those more narrow situations that you had in your research setting. So the two are balanced with each other in good research. This will not be our last trip into validity, but we want to finish up experimental validity here, talking about two additional types of validity. Later on in the semester, when we get into our measurement chapter, we'll talk more about some of these ideas of validity. One idea here of validity is construct validity. We create operational definitions of our variables in an experiment. For example, previously I said healthy eating in our experiment is really the independent variable, and I operationally defined it as eating an apple. But I could have done so with eating something else that we deemed as a healthy snack. You'll also see later on, when we get into measurement, the ideas of constructs, factors, and latent variables, which will tie back to this idea of how we operationally define and understand the construct, the underlying factor, the idea of our experiment, how we operationally defined it in our experiment. We want to make sure we take care in defining our experimental variables in general, so that we can replicate the study in future experiments too. In this situation, it'd be relatively easy for someone to replicate apples. It'd be even easier if I cut the apples and weighed them and told them which type of apple and was very specific. Another form of validity we're concerned with is the statistical conclusion validity. In an experimental course, it's useful to have this here under experimental validity. Sometimes I just include this in the general discussion of statistics. But we want to know what extent a statistically significant result exist between the experimental and control groups for our simple experiment between those that had a healthy snack and those that didn't. But I want to extend this for you all. We're not just looking anymore for statistical significance and p-values. Really what we mean is there a meaningful effect that exists in the experiment, and is it detectable? It's not just reporting a single statistic like saying my results are significant at the 0.05 level. What does that mean? What is the results? What are the effects that we have in the experiment? And are they supported by the statistics that we used? Keep these in mind as we're building an experimental design and quasi-experimental designs. And later on, we talk about non-experimental designs. These two forms of validity are still going to be meaningful in all of our quantitative designs. So we want to make sure we've designed our operational definitions well and that they're replicable, and also that we use the appropriate statistics. It's not just about the outcome, but we also want to make sure that we're using the appropriate statistics in our experiment, that their sample size is large enough, we have the correct measures, our instrument is reliable, etc. So we want to make sure we have all of those nice properties that can support the statistical conclusions that we'll get into in our future lectures on in measurement. We'll talk a little bit more about adequate measures and reliability when we get into sample size, when we get into inferential statistics. We've talked about the criteria for a well-designed experiment and really anchored that in the idea that all of those criteria really help us with our experimental validity. We have our 4 different ideas here of experimental validity. Internal validity is sort of the core of the experimental design. It allows us to say things about cause and effect and believe that our independent variable had an impact on our dependent variable. The extent that things generalize is our external validity. How well do we believe our sample represents the population? Can we make claims to more general events? Construct validity. Did we do a good job modeling the independent variable, the manipulated variable? Did we do a good job defining what the construct, the operational definition, and can someone replicate that? And finally, statistical conclusions or conclusions. Did we use the right statistical models? Or do we have enough data that we can actually make a claim? All of that are sort of the positive direction of understanding validity and understanding the quality in an experimental design. Now we also want to consider factors that could jeopardize in different forms of validity. In your Campbell and Stanley, if anyone's done some extra reading in our experimental and quasi-experimental designs for research, you can probably find some of this online too. But the classic here discusses this in terms of factors jeopardizing internal and external validity, when we'll talk about those as the threats to different forms of validity. We can think about the threats to internal validity as classes of extraneous variables that could confound our study. Our first threat is history. So there's unanticipated events that occur while we're conducting our experiment, and that could affect our dependent variable, our outcome. Not only can a specific event occur for our history threat, but maturation occurs. People grow older, wiser, more experienced during a study. This especially occurs when we'll see studies which have multiple measurements. Speaking of measurement, testing itself can be a threat. The effect of taking a test on the scores of a secondary test can impact our study. You can get test wiseness. Instrumentation. This effect is due to inconsistent use of measuring instruments, changes or that it could occur in our instrument, or just bad measurement in general. With statistical regression, can affect participants who are extreme scorely, and if individuals are selected on the basis of their extreme scores, we see individuals regressing back to their mean, but we can also see statistical separation based on extreme scores can bias our results. Speaking of bias, an effect due to groups or participants not being randomly assigned, we consider this a selection issue with internal validity. That is, the groups are not equivalent to begin with. Experimental mortality occurs when an effect due to participants dropping out of an experiment on a non-random basis. If it were to occur randomly, we would be okay, but this is often not the case, that individuals for have a related reason for dropping out of a study. And then finally, selection, maturation, interaction. So we see maturation not being consistent across a group because of some selection factor. Now, all of these can interact. So we say selection, maturation as a known phenomena, but all of these different threats to internal validity can interact in an experiment. Our threats to external validity impact our ability to generalize to a population. So we may have really good internal validity. Maybe we've gone through and protected ourselves from as many of the threats as we can. But now we want to be able to generalize from our study to the population we're interested in, to those, so that it's useful. Interaction effects of testing can occur, and when those do, those interaction effects is interaction, the idea of testing or being pre-tested with the actual experimental treatment. So the results may not generalize to the population we intended to. So an example here is physical activity is going to be performed in the experiment. If we have a pre-test evaluating individuals, that might prime them to know certain skills or to impact the actual experimental treatment that would not normally occur in a natural setting. When our selection basis and the experimental treatment are interacting, we get the interaction effect of those two. So you can think of this as having high performers in one group and low performers in another group, and those performance is related to the treatment effect. Let's just give an extreme example. If I'm evaluating mathematical performance and I have these intact groups, and not just high or low ability, but just imagine I have intact group 1 in an elementary school and it's first graders, and intact group 2 and it's sixth graders. It would be extraordinarily difficult to see if there was a effect based on my treatment, just based on the selection basis would be swamping the experiment itself. I wouldn't be able to disentangle that from the experiment. Reactive effects of experimental arrangements is that the artificiality of an experiment could impact or threaten the validity. Not just external validity, though we have it listed here, it could also threaten the internal validity of our experiment, the findings that we have. Imagine you're expecting a classroom setting, and we've set up a room where everything is backwards, where instead of the teacher being at the front of the room, the teacher teaches from the back of the room with everyone's backs to them. It's a pretty extreme example of the structure of a classroom, but that would be an artificial result that might impact the validity of our experiment. Our last threat to external validity is a carryover effect. It's multiple treatment inference. So you can imagine if you have more than one measurement of a treatment, we'll see this in our repeated measures designs we're getting to, that this carryover from one time to the next, one measurement to the next, can occur. I had this happen in a very simple experiment where we had pieces of colored paper, yellow, blue, purple, red, and they were scented with different flavors. So yellow was lemon in the baseline group, and red was cherry, and purple was grape. And when we went through, we then in our second condition, our next treatment, we mixed up some of the colors. Not all, but some of the colors. So now sometimes yellow was cherry and purple was lemon. And we've certainly found, especially in that second go around, that lemon had a very strong scent and would carry over. So even when the next page wasn't scented lemon, people still smelled lemon. And also people tended to mix up certain scents because the visual cue and the scent cue no longer matched each other. Our threats to construct validity occur in several different ways. One of them is simply we have an inadequate pre-operational explanation of our construct. So this will occur when we do not define well what our independent and dependent variables are, so that if we have, especially when we have multiple participants like we do in often in education, when we have multiple classrooms, teachers may implement a very different instruction to students for the treatment and control groups. Our mono-operational bias is that we only have one form of the experimental variable. In our example with apples, I've already sort of gone into this threat, a construct validity threat, is that if we had healthy eating and we only have a control group with no snack and then a control group with apples, there might be impacts based on just simply eating, and there might be impacts of different types of healthy snacks. Different types of fruit may have a different impact, and different types of vegetables. Perhaps there's an interaction going on with our sugar versus non-sugar. But also when we don't define that, if we were to simply limit only one level of our experimental variable, there could be a threat here to our construct validity. Just like when one form of the independent variable is presented with mono-operational bias, we also have mono-method bias, which impacts our dependent variable. This would occur in more complex studies when, think about your psychological studies, if we're evaluating happiness and we just had people report on a very short survey about the outcomes of their happiness, when there's other mechanisms, whether they be observational, video observational, live observation, self-report in a written feedback, other ways of capturing that information that may be appropriate as well. I feel like this is also a really good time to remind you that all of our threats collectively are balanced. So it's nice to have multiple measures of our dependent variable or multiple forms of the dependent variable and lots of different experimental conditions, but we need to balance that with simplicity and other issues that can occur in our experimentation. So all of our threats to validity and all of the positive qualities in validity and criteria for well-designed studies should be balanced. Hypothesis guessing occurs all the time in experimentation when somebody, based on being in an experiment, will act differently, and because they know that they're part of an experiment. Somebody may try very hard or may interact with some element of your study. And finally, confounding constructs and levels of those constructs. We draw conclusions about variables when some level of the construct could be absent. So if we have our condition where our study where we have no snack and then a healthy snack, which is apples, there's no condition where we have a unhealthy snack but someone is still eating. The threats to construct validity just simply help us think about what a well-defined construct should be. The outcome, the levels of our construct, whether or not the claims that we can make are really about the outcomes that we're interested in. So my little experiment, no snack versus a healthy snack of apples, I want to make a claim that healthy snacks had an impact, and somebody says, no, just any snack would have an impact. Well, there's a confounding issue there that's real, that there's a real alternative explanation to my hypothesis. First on our list of threats to statistical conclusion validity or just conclusion validity, first we have low statistical power could be a threat. That simply means you have too small of a sample size to detect the effect that you're looking for. More especially, a statistical power, we'll learn more about this later on in the semester in our statistics section, but we can think that we have an effect that we should be able to find, so we need to have a sample size that is adequate to find that effect. So when that effect should really occur, we should be detecting it. Low statistical power occurs frequently. Often there's interactions that occur because we just simply cannot get enough participants, or perhaps there's financial constraints or other reasons. We have statistical tests which have robustness to the assumptions they make. So maybe they make assumptions about normality and other features of the statistic, independence, etc. We'll learn more about some of those when we review some statistics. However, violating the assumptions can impact our conclusions. There's extreme violations and there's violations that are within the robustness of the assumption. But for example, if you try to report gender or ethnicity or some qualitative variable on a numeric scale, and you try to find an average of those, you're violating an assumption of a test. We know that p-hacking occurs, or phishing, or error rate problems. So significance testing used to be so coveted that people would look for any statistical difference to report. Nowadays, there's a lot of, more especially from the Association of Statisticians in the United States and across the world, there's really a pushback on just reporting a p-value, just reporting a significant level. People really want to know what the effects are of your study, both raw effects, differences in means, and things like that, and standardized effects we'll learn later on in the semester. But the pushback is that you don't just report something as significant, and you don't just search your data for significance. That would be a violation of the way the statistics are used. And finally, we'll also consider reliability of measures. We'll consider this again in our measurement section, our measurement chapter. So make sure that the techniques that you're using to measure individuals are actually effective and current. This is usually a fun in-class activity. We take our hypothesis statements, some we've worked with before. You can come up with a new one, whatever you're interested in, but make sure you have an independent variable that you can manipulate in your hypothesis statement and a dependent variable. Go back and review the criteria for a well-defined experiment and pick two of those criteria. You can pick more if you want, and see how those apply to your research and discuss how you might incorporate these criteria into your research design. Also do the opposite. That is the opposite. We have criteria for a well-defined experiment. Think about the threats to validity that could occur. So here I say at least two unique internal and two more external validity threats. You could pick some statistical conclusion threats or construct validity threats. Pick some of the threats that can occur in our experimental design to validity and apply these to your research ideas and discuss how you might prevent these threats. This would be, you could use this as an alternative activity instead of summing things up. When you go online, sometimes I know that on our Blackboard site, individuals have already summed up a chapter a few times or the lecture a few times. You want to do something a little different. So this is a different opportunity for you to get full credit for your assignment. And also it's useful for you because as you're going through later on, when we are more formally going through our projects or writing up a new proposal or paper, this will help you with your current research ideas you might have. We have done a lot of work building up to experimental designs, and partly because once we've done all of these things, we understand threats to validity, we understand what is criteria and quality aspects of research. The design aspects is just a structural element. There's still important features of our experimental designs we should know. One thing we can do is represent via diagrams, symbols here, the experimental variables and the conditions. These symbols are arranged to reflect experimental approaches to conducting the study. Now, in practice, you might go through and create a design, especially for our course, but also in practice, you might go through and create a design like this, but you don't necessarily see this reported in the journal articles. They report this verbally. So just from a perspective of our methodology section, you will report each element of these designs, but you don't necessarily have to show the actual symbols. But the symbols are very helpful when we go through and try and construct our experimental design. Just a note here that the subscripts that are going to be used, these are used with the grouping and experimental and control variables to indicate the levels of that variable. In the case of the experimental variable, we'll see that subscripts represent the different levels of treatment, which are called the experimental treatment. And we have controls as well, but the experimental treatment effect. And it is also worth noting that we measure the dependent variable, that outcome. So when we see O1, O2, that is a measure of the dependent variable. We can start off by keeping this relatively simple. R is for random assignment. In our true experimental designs, we always want to be able to randomly assign to groups. So the R there represents random assignment. We will see later when we get into quasi-experimental designs and non-experimental designs that will change. Group is which group you're in. Again, I reference you to those subscripts. Group 1 could be experimental treatment, the treatment effect, and group 2 could be experimental treatment, the control effects. We can think the apples and no snack for our healthy snack experiment. X, this is our actual experimental variable. This is the independent variable that we're interested in. So in this case, there's an X for group 1. They received the treatment effect, and there's a dash there that someone did not receive the treatment effect. So that would be no snack, those two dashes, and the X would be that they received the healthy food, which was healthy snack, which was an apple in there. It's a very simple experiment. And finally, our outcome variable, that's our dependent variable. It's really worth noting that what we care to measure is the dependent variable. So we want to measure the dependent variable for group 1 and the dependent variable for group 2. The reason it's an O is because outcome variable is probably more broad in some ways than dependent variable. And also, I didn't invent the symbols here. This is just the standard symbols that individuals use. So these symbols are going to help us build some of our experiments. We'll see some adjustments to these and we'll build on these. But those 4 symbols, R for random assignment, G for group, X for our independent variable, and O for our dependent variable, will help us design some experiments. Here are our commonly used experimental designs. A post-test only control group design, pre-test, post-test control group design, Solomon's 4-group design, which is actually a subset of the factorial design, and a repeated measures design, which can be extended out in a time series design. So we'll go through each of these. Of note, there's also other types of designs. You can have a one-shot case study, which is better. It's as opposed to experimental design, might be more of a qualitative research design. Same thing kind of with a one group pre-test, post-test design. You don't have anything to compare it to. Just have one group with a pre-test and then that same group takes a post-test. That might be interesting to explore more qualitatively. Also, just kind of going through if you find differences. For example, if I found a school where they had no snack and a school where they ate apples, I didn't have any control initially in setting up those schools, so there's so many confounds in there. That would not be any sort of experimental design. It would be more of just an observational study, and we can talk more about those later on in a couple lectures. Historically, those first 3 experimental designs sometimes are referred to as true experimental designs, with the invention of some more modern statistics. So we can extend that a little bit. So our post-test only, our pre-test, post-test control group designs, our Solomon 4-group designs, classically were called true experimental designs. Now with some of the modeling that we can do in controls, factorial designs and repeated measures designs can still be considered a true experiment. But just so you know, if someone says, what are the true experimental designs? Those first 3 were classically considered to be true experimental designs. Our first design is the post-test only control group design. This is a very simple experimental design. Remember, simple is not bad. We want the appropriate level of complexity for our studies. So in this basic design, we involves just two groups, a control group and a treatment group, a treatment 1 versus treatment 2, but it's just two groups, G1 and G2. Those R's there mean that there has been random assignments to groups. Without it, we really don't have an experimental condition. We just have an observation of what is occurring. So random assignment must occur. That's the R in their symbol there. And groups are compared on some outcome. So each group has an outcome. Outcome for group 1, O1, and outcome for group 2. Now I know seeing the symbols can make us sort of have a existential moment here. So why don't we put this in a concrete example? I sometimes take for granted that we're all having our pause moments and taking a moment and putting our own research in front of us, but make sure you do so with some of these designs. That way you can see the designs you want to build and how they impact your settings and your structure of your research. I'll go through obviously an example or two that we've seen before. Let's use our very basic post-test only control group design experiment from before for healthy snacks. We have a treatment and a control, but notice here our design is flipped. So let's go ahead and do that. As long as we are consistent through the experiment, we can have the dash for our control group first and the X second. So as long as we keep organized here and we know what things represent, we know that X is our treatment and the dashed marks, the no treatment effect, is our control group. So let's just put this in more context. Just spread these out so they fit evenly in the experiment that we've seen earlier. So we have the no snack treatment. Group 1, G1. Those students were randomly assigned to that group. They get an R, so it's R, G1. We test their performance for group 1, O1, the outcome, the dependent variable, and we label that O1. Then we have group 2, also randomly assigned to that group. X is the treatment effect, apples, and O2 is our performance or math test 2 for those individuals. So we'll just overlap this. The dashed group is just our control group, no snack. The X is our treatment effect. That's the healthy snack. That's the apples that they receive. So our post-test only control group design randomly assigned 60 participants total to two groups. 30 went to group 1 randomly and 30 went to group 2 randomly. Group 1 received no snack before the performance on their math test occurred. Group 2 received a healthy snack of apples before their performance on the math test occurred, and then we measured them. O1 and O2 are the measurements for each group. That is the post-test only control group design, our first of the experimental designs and the simplest of our designs. And if you understand this, you understand the way the symbols are working here, it makes it a lot easier as we get just slightly more complex. The pre-test, post-test control group design is one of the more classic designs. Often it's what we think of in psychology and education when we think of an experimental design. It extends the post-test only control group design. Not necessarily better. Remember, simple and more complex. If simple is appropriate, that's fine. Our participants, same thing. We randomly assign them to groups. Groups are going to be compared on some outcome. The difference here is that we're adding a pretest. This pretest doesn't ensure that randomizations occurred, but if there's a difference between the groups, if for some reason they're still not equivalent after randomization, we can detect that. And we can add a measure of statistical control. When we call these, when we look at the scores from pre to post, we call that a gain score. This is what our design looks like now. It's almost identical to the last design, minus an additional measurement here of the O's, and some of the subscripts have changed a little. So let's break this down in an example. Just to be very specific, before I show an example, our Apple example, a pretest is prior to the treatment being administered, and a post-test is applied after the treatment has occurred. So in our last design, it was a little bit more self-evident. We applied the treatment and then the post-test occurred. Here we're going to have a pre-test before treatment, prior to treatment, and a post-test after the treatment and control have been applied to our students, to our participants. Here's our post-test only designed as a reminder. Random assignment, group 1 and group 2. Treatment effect is the apple. No treatment, no snack is the control. And we're exploring the outcomes. So we'll flip this around. Instead of using the table, we're going to use the design, the symbols, and then we're going to add a little to the symbols to give it context. Let's put some language around the symbols for our pre-test, post-test control group design. Remember, pause and go back if you get mixed up with some of the symbols, but I'll try and go through them again. I like repetition as we go through. Our R, we've randomly assigned. We've randomly assigned individuals to groups. G1, G2, we had 30 participants in each group. In group 1, they're still the group. In this case, they've received the healthy snack, which we're operationally defining as an apple. And group 2 did not receive any food, thus the little sad face there. They didn't have any snack, and we're going to compare the difference between those two. O1, dependent variable measure 1, and dependent variable measure 3, we're calling it. We're keeping those in line. We'll see in a second why. We have a pretest. The pretest for group 1 and the pretest for group 2. This must occur before the treatment happens or it's not a pretest. In other designs, you can see where you can have multiple post-tests. But in this design, very simple design still, a pretest. And in this case, it's going to be a measure, pretest measure of mathematics so that we can see a gain score if something were to occur on our math test. So our outcome measures, O2 and O4, are our outcomes, our dependent variables after that treatment has occurred. So here we're just keeping things in a line, right? If we read across line 1, R for G1, randomly assigned to group 1, their first measure is a pretest, O1, dependent variable 1, prior to the treatment being administered, X. That treatment is apples. We then measure them again with our post-test, the math test, the performance on their math test. We label that O2. We then go down to the next row, randomly assigned to group 2, RG2. We examine them on a pretest of mathematical ability. That's assigned O3. Their condition they're in is no snack here. And then the final O4 is their performance on their math test. I know as we go through and we think about these and reading our text and going through the examples, it's always nice to have extra examples. So I'll try and fit one in here. An example 2, same structure, right? We still have R randomized into 2 different groups, group 1 and group 2. We still have a pretest, O1 and O3. That's the first measure prior to the treatment, which is X and dash there for no treatments. We still have randomized, 2 groups, pretest, treatment effect, and then after that, a control. So it is the pretest, post-test control group design. We're just going to fit it in another research setting. So I have a question or idea in mind about the effect of martial arts classes through adolescent drug education programs on behavioral outcomes. My hypothesis, at least my first run of hypothesis, is martial arts are more effective than standard care in deterring and delaying substance use through middle school. We'll see as I start to define these characteristics, these variables and independent, dependent variables, the treatment effect. I'm going to refine this a little in words for you, because I have to narrow down what I mean operationally when I say these things. So first, we have an experimental variable. That experimental variable is actually adolescent drug education program. I label it as martial arts class are more effective than standard care, but it's the type of education program you're using. And I will specify that we will have martial arts classes, or that'll be the martial arts classes will be our treatment effect. Standard care will be our control group effect, and we will specifically have 12 classes over 6 weeks here. So now I have my experimental variable. I'm going to control the type of program individuals my students are allowed into. We're going to randomly assign them to group 1 and group 2. They will be given a treatment, which we're going to consider the martial arts class, and which is our X, and our control, which is the dash, which is our standard care. You may also just note that standard care, you might also control treatment versus treatment, right? We could give no care at all, and that could also serve as a control. So we also have then the independent measure, a second independent measure to think about. We can think about our pre-test, post-test as another independent measure. It is a pre-measure of adolescent behavior. We have the prevalence of recent use. That's our O1 and O3 in that above symbolic design. But we're doing a pre-test, and we can call that another variable, independent variable, because we can look to see if there's been a gain score. We're actually measuring a score of from pre to post. And specifically, I might give this a little bit more depth and definition, because it's not just anybody I'm going to allow from middle school over the course of their entire middle school career, because I wouldn't have time to conduct that experiment, or potentially we would slip into some of our other types of designs. So we might say that 1 month after school starts, we begin our 12 classes, and at the end, we will have our true dependent variable, our dependent measure here, which is going to be our post-test. That's our O2s and O4s. Now, our measurement can be taken twice, right? We can have the same, let's just say we have a self-report survey. I know we don't always like self-report surveys, especially with younger students here, but you could have a self-report survey. You could also conceive of other ways of trying to track substance use through schools, reported use, etc. The key here is that we have a pre-measure, our O1 and O3 for groups 1 and group 2, and then our post measure, O2 and O4. That's the post measure of adolescent behavior. And that will be done after the final education programs are done. So that way we have some limits here, we've added more substance, and we've thought through our research hypothesis a little bit more. I might even refine it in the hypothesis, say things like 7th grade specifically or 8th graders specifically, and go through and refine our variables as well. The pre-test, post-test design, I briefly mentioned before that it allows for gain scores, and I called that another independent variable because it gives us some more control. Remember, our independent variables are about adding some control here. We're not manipulating the pre-test and post-test, but we're manipulating when they're administered. And through that, we can observe the gain score and use that to add statistical control into our research. So let's just say in this example that we test students at the first time in the pre-test, and we see that there's no difference between the two groups. We test them in the post-test, and there's a difference between the two groups. My hypothesis is right. The martial arts classes outperformed or improved delaying substance use through middle school. Well, we have a little bit stronger evidence to suggest, well, these were not just randomly assigned, but they also started at the same place. Now imagine that our outcome is a little different. That group 1 starts off with a low substance abuse level. Their pre-scores, their pre-reports are very low, and group 2 is very high. Just through random assignment, this could still occur. Chance events still occur. Then we look at the post-test. It's going to be a very different post-test for us now, a very different understanding. If we see from group 1, which started off low, they stay low, and group 2 started off high and they stay high, that is, they stay with more substance use in this case, potentially, then we're not really that impressed by our outcomes. Conversely, if we see that the outcomes look exactly the same, the outcome measure, the dependent post measure of adolescent behavior is that we look at them and delaying substance use, we see that reported wise, they're both relatively low. But then we go in our pre-test and we see that in group 1, they started off higher, or they started off with more reported substance abuse issues than group 2. there's actually been effect that we wouldn't have determined in a post-test control group only design. Now we have the pre-test to help us statistically control for gain scores that might have occurred. And there's different ways. When we get into actually some of the analysis of this, we'll take a look again at this type of design from a statistical process and a statistical view. So let's go ahead and do our first extension of some of our models, just taking the first two designs. Our first one is the post-test only design. Remember, these designs are very similar. So the post-test only, we give a treatment, we have a post-test, but now if we wanted to, we could have a whole bunch of more groups, as many groups as we could functionally have or practically have in our experiment. We still have to randomly assign for each group, group 1, group 2, group 3, all the way down to as many treatments as we want. We'll call treatment K. So you can go down to, if we want 5 treatment effects, we could have group 5 as our 5th treatment, and we can still have a control, group 6. Some people just consider the control group another treatment. I often just do that. But in this case, we can just see where we can just keep extending, having more groups. Let's see a practical example instead of confusing ourselves with the subscripts. The subscripts are just K number of treatments, and we'll see that that'll be relatively easy to clean up with our 3-group example. So we have group 1, group 2, and group 3. Previously, we've seen group 1 and group 2. So we might still just think back. You have group 1 is randomly assigned to that group, 30 students. They receive an apple. Now somebody brought up, well, maybe it's just the number of calories. So now we measure out the amount of apple, and we also give chocolate bars. We give chocolate to group 2, something we would probably most consider an unhealthy snack. Of course, making sure you get parental permission for all of this and keeping with all of your ethical considerations, especially if we were dealing with students in a middle school environment. And finally, our last group is going to be our control. You can rearrange these. If you rather call group 1 the control, that's fine. Just make sure you keep everything straight. So our 3 groups now each have an outcome, outcome 1, outcome 2, outcome 3. This is just a way of thinking about post-test design from symbolic structure. And we could have a group 4 if you wanted a potato chip group. We randomly assign people to a 4th group, and now we have a potato chip group. And group 5 could be pretzels, and group 6 could be, crackers. And you could keep going on and on, adding groups as much as it's reasonable, remembering sort of parsimony, simple is good, as long as it meets as long as we try and get the criteria for a well-balanced experiment in place as much as possible, and also try to reduce the threats to different types of validity. Our pretest post-test design is just the same thing, except we add a pretest. The numbering looks a little funny down there because we have 2 measures. So instead of K, we see things like down in the random assigned group K, which is our last treatment group. The observation now is 2K minus 1 because we have 2 observations that have occurred in each condition before this. And then we see the last pre-test, post-test is 2K. So if you have a concrete example here, like we'll do for the same type of experiment. So now we're in our concrete example of having 3 groups, same design, our apples versus control. We extend that to add in our chocolate bars. So now we see group 1, we get a measure at time 1, the pre-test, a measure at time 2, the post-test. We call that O1 and O2. Then we go to group 2, measure of time 1 pre-test is O3, and the measure of post-test is O4. And then we go to group 3, the measure of pre-test is O5, and the measure of post-test is O6, just in order to keep our data straight. Often you're doing this in different types of software, maybe it's Excel or some other database package. So you're kind of keeping it straight that way as well. But this is symbolically keeping it straight. Don't obsess over any of the subscripts if you have trouble with them. Put them into concrete examples, and you'll be able to just follow the same method of extending out pre-test, post-tests, and those observations by rows. So probably for a lot of reasons, this is a good time to pause. Make sure you're keeping up on your designs. Take a moment. If you've been just having 2 groups in your design, extend it to 3 groups and go ahead and model what your groups would look like and your treatments and controls would look like symbolically. But also go back to your research questions and your hypothesis. Go back to your constructs, the operational definitions that you're working with, and go back and try and redefine those for a new design where you've extended out, you've added more groups to either the post-test or the pre-test post-test design. Now that we've gone through our two classic designs, the post-test only control group and pre-test post-test control group designs, we're combining those two. So now we're going to have 4 groups instead of 2 in our design. So again, participants are still randomly assigned. So there's still 4 groups. You are still randomly assigned to one of those 4 groups. The idea here is that it's all in one experiment. The effects can help us determine by comparing the post-tests of the experimental group, the 2 experimental groups, to really try to determine if maybe treatment might be impacted by pre-testing. So we can test to see that if the treatments aren't the same based on our pre-test being introduced into our experiment. If we go back and look, we can see some of our threats to validity that are impacted by pre-testing or the act of testing. So we can explore to see if that's occurred. So we're going to test the effect of pre-tests. In here, we are going to have now in our Solomon's 4-group design, we have 2 controls and 2 experimental conditions. So group 1 and group 3 in this case are both X. They both are our experimental groups. Only one of each of these 2 types receive treatment. The 2 types being whether or not they're post-test only or pre-test post-test. So group 1 receives the treatment and group 3 receives the treatment, but group 3 does not receive the pretest. So we can test to see if there's an impact on their outcomes based on the pretest. All 4 groups though receive the post-test. So we can think about this as stacking those 2 designs together, and let's see what that looks like. So let's just start with our pre-test, post-test section of the Solomon's 4 design. It's just what we looked at before. We still have random assignment to groups, group 1, group 2. We have pre-test prior to having the treatment of apples and no snack. Apples for group 1, no snack for group 2, and then a post-test, a math test, our final outcome measure we're interested in. Now we add the post-test only to this same experiment. So now we have 4 groups. Even though it says G1, G2, I'm just stacking those 2 together. And we still have, in that post-test only design, a group that gets the treatment and a group that gets the control, a group that gets healthy eating snack apples and a group that gets no snack. And now we can test the difference between pre-test, post-test. So just to solidify this, we take the 2 designs and meld them together. It's now 1 design with 4 groups. We have to randomly assign to all 4 of the groups, group 1, group 2, group 3, group 4. So that's our first step. We've randomly assigned individuals to their future conditions. Our group 1, group 2, we still assign treatment and control. So group 1 gets the treatment effect, the apple, the healthy snack. Group 2 gets nothing. Group 3 now also gets the healthy snack, and group 4 gets nothing. They're the control group. The distinction here is that group 1 and group 2 both get the pretest. And then finally, everyone gets the post-test. So in some ways, you can look at group 1 as a double treatment effect. They receive both a pretest. Imagine in a world where the pretest matters. Imagine that the pretest will impact your final score, that in an extreme way, that the pretest and post-test on this math exam are identical. You could think about this with your quizzes. What if all the quizzes were pulled together and became your final? You would have had a pretest and a post-test that was identical, not just similar. Having had the pretest would greatly impact your post-test, or should, in theory, greatly impact your post-test. So I hypothesize that, and that's the concept behind the Solomon's 4-group design. Group 1 gets the treatment of pretest and the treatment of apples in this case, which is the treatment effect. And group 2 gets the pretest, but they're the control for our real experiment, which is the difference between healthy eating and not eating prior to taking our exam. And then groups 3 and 4, they also act as a control. So now we can disentangle whether or not the pretest had an impact in our study or not, which in many studies in education and psychology, this type of effect to try and understand either whether there's a baseline to start with or whether there's an effective pretest is meaningful. One last way of looking at the structure of the Solomon 4 control group design. So here's our design, and here's some of the questions we're really asking is, what is the effect of treatment on the outcome? In our example, that was type of whether you get a snack or not, healthy eating, an apple or not, or the control. What is the effect of pretest outcome on our outcome? So did you get the pretest or not? And then is there a significant interaction between the treatment and pretest? Now that we have explored both, we can treat both, even though we're interested in our main hypothesis question of healthy eating. We now can explore whether or not treatment also had an impact, because we treated it as if it were an independent variable, even though it's not really the experimental variable we're interested in. So I'll just put this in this type of conditional table. This will be helpful later on. So this is time 1 and time 2 when we look at this in our statistics section. This will help out a little in understanding how we're pulling together just our outcomes. I'm going to ignore O1 and O3. Those are our pretests. I'm just going to use them as if they were their own effect, which they are. So if I look across the rows, treatment, those that received the treatment and have outcomes for are O2, our group 1, and O5, our group 3. So those two together, if I combine those both receive the treatment effect. Then if I combine O4 and O6, that was group 2 and group 4, just their outcomes. I combine those two, and that's no treatment effect. So I could combine those, and I can look at, for a main effect of whether there was an effect of treatment versus no treatment, I can combine group 1 with group 3 and look at that combined toward the combination of group 2 and group 4. I can do the same thing with pretest. I can pull together group 1 and group 2 outcomes, that's O2 and O4, and group 3 and 4, pull those together and look at the difference between those combined groups. So the first one, the first main effect of treatment, answers the question, what is the effect of treatment on outcome? Well, both of those groups, group 1 and group 3, they received treatment. Both of those groups, group 2 and group 4, did not. So I can look at answer the question, what is the effect of treatment on outcome? I can then look at the main effect of pretest, combine groups 1 and 2 versus groups 3 and 4, and I can say, what is the effect of pretest? But I can also see if there's an interaction effect. And usually the interaction effects can be most interesting, because if potentially there is both a pretest and a experimental interaction going on, I might see very interesting performance at what we would consider the interaction level. So if I go down the column of pretest and across treatment, O2 received both, we might see a difference in that than we did in any of those other conditions. Group 1, group 2, group 3, and group 4 might be different. So it's interesting. We can answer all 3 questions. We're not just answering 2 questions here. We can actually answer 3 questions this way. Factorial designs open up an entire world of designs to us. We're not really limited anymore by just pretest, post-test, or one independent variable. And we'll see, looking back, that the Solomon 4 group design is actually the first of our factorial designs. There's not just one independent variable that treatment we're interested in, but we also introduced a second independent variable, which was our pretest. So here our factorial designs, you could think about as an extension of that, but we're not going to worry about pretests anymore. We can have any other independent variable. So our factorial designs, things are still the same in the sense that we have participants randomly assigned to groups. Groups are going to be compared on an outcome, but now we want to understand the effects of 2 or more independent variables on a single dependent variable. Some of the benefits of this is that we can investigate complex studies. We can see interaction effects and main effects of multiple variables on our single outcome variable, our single dependent variable. We can control confounding variables if we find there's an effect, or we believe there's an effect ahead of time for another variable. We can introduce it as another independent variable, even though it's not the true experimental variable we're interested in. And it reduces error variance. We control by adding another independent variable into the model. Each independent variable we introduce has its own levels. So we can explore those individual levels, and we can also explore how those levels interact with each other. So our first design, and the simplest design we'll look at, is a 2x2 design. This is the same structurally as the Solomon 4 groups design, but not with pretest. There's no pretest necessarily in a factorial design. We call the simple structure a 2x2 design because there's each of those numbers is a placeholder for an independent variable. So the first 2 is variable 1, which will have 2 levels. The next 2 is variable 2, which will have 2 levels. So it's a 2x2. If variable 1 had 3 levels and variable 2 had 2 levels, it would then be a 3x2 model. So that simple symbolic structure looks hopefully similar to what you saw as the Solomon 4 groups design, but instead of pretest, we now have a second independent variable. So our symbols here, G is the same and R is the same. We randomly assign participants to 4 groups. Same thing we've done before. Our outcome, we still have a dependent variable. O1 through O4, we have 4 measures, 1 for each group. Group 1, outcome 1. Group 2, outcome 2. But now we have 2 independent variables. Just for simplicity, I am going to be calling them X and Y. Also, I think this is relatively consistent with what you might see in other locations. So X is the treatment. We can think of this as primary interest. You might be genuinely interested in both independent variables, but for now, we'll just call X as the primary interest and Y as the secondary independent variable. So we have 2 independent variables, and we have 1 outcome, 1 dependent variable. Now we see that group 1 receives treatment 1 and is level 1 of the first independent variable. Group 2 receives treatment 1 and is level 2 of the second independent variable. Group 3 gets treatment 2, maybe our control, and is level 1 of the independent variable. And group 4, also a control in this case, if it's our primary interest, it's X2, and also the second level, Y2, of our independent variable. So when going through our factorial designs, we can get more complicated. You can always come back to this basic structure for all of our research designs to know sort of how to begin extending our models. And we can have more groups, and we can even have more occasions. Right now might just be a good idea to run through a couple of verbal examples. We'll still show the symbols up here. We have 2 independent variables and 1 dependent variable. The effective teaching strategy, perhaps that's our main variable of interest, we'll just call it X, and gender, which we'll call Y, on student achievement. Student achievement is our outcome, our dependent variable. We are going to partition our experiment with having 2 independent variables. One is our true experimental variable that we're really interested in manipulating, teaching strategy. The other one we can't manipulate, but we're going to add it in as a control and treat it as if it were an independent variable, which is gender. We'll do the same thing here. We're interested in the effect of a particular counseling technique, X. You can think of different therapies, different methods of counseling, and the client's ethnicity on the success of the treatment. So success of the treatment is our dependent variable, our outcome variable. We care really about this different types of techniques. We can control those. That's what we're going to manipulate, and we're going to add in client's ethnicity as a second independent variable. If we want, we can have multiple techniques and multiple ethnicities or multiple gender categories. We can add other groups to either independent variable. For now, you might just keep it thinking about it simple as a 2x2 factorial design. And finally, another talked through example here is if we had the effect of martial arts classes, X, and children in 2 age groups on the ability to perform certain physical tasks. So we might be interested in martial arts ability, there are multiple martial arts classes across multiple age groups. We don't control age groups. We're going to model it as if it were an independent variable. And perhaps the physical tasks we're interested in are related to some performance in some other sport or activity. Maybe we have a hypothesis that martial arts makes you better at helps you improve performance in dancing or basketball or another sport activity that could be related these children are doing. So in general, we can think of all of these as factorial designs, all of them having a very similar structure of design. This is a great opportunity for you to add your own design here and start thinking through what it would be like if you had multiple independent variables. So our first time through with factorial designs might be a little complicated, and we're going to make it more complicated, but let's go back to something familiar. Believe it or not, a factorial design of 2 by 3 is something we've seen before. When we, in our previous lecture, talked about having our healthy eating hypothesis, that we believed that students would perform better with healthy eating, like snacks such as apples. We also compared it to chips and to a no snack condition. We had 3 different possible conditions. We also broke it out by boys and girls. We wanted to compare boys and girls for each of those conditions. So same type of thing. Everything's still randomly assigned. Individuals are still randomly assigned to a group. We have, in this case, 45 boys and 45 girls in the entire pool of our sample. We randomly assign all of the boys to 3 different groups and all of the girls to 3 different groups. Each group still gets some form of treatment for either no snack, apples, or chips, and the 2 groups are split by their genders of boys and girls in this case. So our design is modeled with a true independent variable that we're really interested in exploring, type of healthy eating. It has some impact on our outcome, still, math test. But we also wanted to see whether or not there was a differential impact based on boys and girls. So we treat that variable as another independent variable, even though we can't control it. We still treat it as one in our study. So in this design, we actually have a 2 by 3 design in that we have 2 genders assigned for boys and girls, and then we have 3 levels of our independent variable assigned for different types of healthy snacks, which is something we can actually control. Another way of understanding the factorial design is the same way we did with the Solomon 4 groups design. What is the effect of treatment on outcome? Now, instead of pretest, we have a second independent variable. So what is the effect of independent variable on our outcome? And what is the interaction between those two, the treatment and independent variable? So we can think of this as our healthy eating as our treatment effect, and our difference between boys and girls as our second independent variable. I have up in the right-hand corner, just for your reference, the Solomon 4 group design. And here we have the factorial design. We have our 4 groups. Instead of pre-test, post-test, where we had in our Solomon 4s O1 and O3, we now have X1 or X2. So that's our different. Before in Solomon 4 was you get the pretest or you don't. Here you get X1 or you get X2. You get 2 different levels of that variable. And we can put it in the same structure here. So let's just consider our main treatment effect for now to be the Y. So whether or not you receive, in this very simple model, would be apples or no apples. So the treatment group would be Y1. So every group that gets apples, Y1, is our treatment group for our main independent variable that we can control. And we would look through our design. We see that group 1 receives treatment 1, apples, Y1. And group 3 also receives our treatment effect, apples. And that's our outcome there is O3. So we have O1 and O3 are the main effect of being in the treatment group, receiving the healthy snack. And then similarly, we go through, we see Y2s is group 2 and group 4. Those are the no treatment group. Those 2 groups combined form the groups that did not receive apples. Imagine saying that we're not worried now about the difference in our second independent variable, gender, boys and girls. We just collapse over them. We look at all boys and girls that received the apples and all boys and girls that did not, the treatment versus the control, and that's what we call main effect. Next, we can do the other direction insofar as we can look to see who's in independent variable 1, and that's all our boys are in group 1. So those X1, so their group 1 is also X1, and group 2 is also X1. We can collapse over those and form this main effect of independent variable 1. That's all the boys, O1 and O2, and all the girls are O3 and O4. That's group 3 and group 4. So we've collapsed over all of the types of effects just to pull together all the boys. Doesn't matter whether you receive apples or no apples. We want to see if there's a main effect difference between boys and girls. Then each one of those individuals, we can look to see if there's a treatment effect. Is there some sort of interaction that's going on? So more specifically, I mean in each one of these cells, when I talk about the interaction effect, each one of these cells, O1, O2, O3, and O4 will have a value. So it might be that we might see a difference in boys, whether they receive the treatment or not, and not see a difference in girls. Or conversely, maybe the girls have a larger effect than the boys. We see that the boys have no effect regardless of which type, whether they have snack or no snack, and the girls do. If they have a snack, maybe their performance is greatly increased or decreased, potentially, depending on the direction of our results. So that's when I say the individual level, we can look at the main effects here across different levels of our other independent variable or treatment, or we can look in the individual cells to see whether or not there's some sort of interaction going on. The repeated measures design is a very popular design, especially as we begin to see our shift away from experimental designs to quasi-experimental designs. This is still under the experimental design structure, but we're going to see that it's much more popular when we look at it from a quasi or non-experimental design. So just because we see the factorial design in this lecture and the repeated measures design, we are going to see those structures again. So this is just the first time through, and the repeated measures design and time series we'll really talk again about in our next lecture. So the repeated measures design, we can consider delay or the duration of an effect. It includes same thing as before with experimental and controls or multiple treatments that we're interested in. But now we're going to have repeated measures of our outcome variable, our dependent measure. So participants are still randomly assigned to their groups. That hasn't changed. And we still have groups which we're going to compare on our outcomes. Our old model for this we can think about as our post-test only design. We had our randomly assigned to one of two conditions. We had a treatment, we had a control, and then we had an outcome measure for each. Now we just extend that. So for group 1, instead of measuring them once on the dependent measure, we now measure them 2, 3, 5 different times. We measure them repeated amounts of time after the treatment has occurred. And for group 2, we measure them along with group 1, and they've had the control. In this case, with our simple example of apples versus non-apples, X, we would have potentially a test, one administration of a test, and maybe 3 short pop quizzes. And for group 2, there would be one administration for group 1 with the apple, and then maybe 3 short pop quizzes. And then you can see group 2 and then same 3 pop quizzes to see if time has an impact or repeated measures distance from the experimental condition. Perhaps by the time you get to quiz 3, there's no difference because of the time effect and distance from the snack. We'll just have one more extension for today, an extension of a combination of the repeated measures and pretest post-test design, just like our repeated measures design. So it's the exact structure, except the experimental treatment can be inserted between measures. So we can have, you can think about it either from the perspective of our pretest post-test. We still have random assignment. We have 2 groups. In this case, you could have more than 2 groups, but in this case we have 2 groups. You have the treatment control group. We have the control, which is no snack, and from our running example with apples, and our treatment is the apples. And now we can have a pretest for group 1, have the intervention, the treatment effect, and then have multiple post-tests. And then for group 2, same thing. We have a pretest at the same time of the pretest for group 1, have no intervention or an alternate intervention, and then have post-tests. This is getting into the time series designs, and they get a little bit more complicated, but also we'll look at some of those again when we get into our quasi-experimental designs and non-experimental designs. So example of our repeated measures and also our time series designs here too. So what is the effect of a leadership workshop on students' social skills? Are there significant differences in social scores at 3 times of measures: before, immediately after, and 3 months after the workshop? So really this would be more of a time series design because we're looking at the pre-test of before, we get a measure before, and then 2 time periods afterward. Another example of a repeated measures design is what is the effect of martial arts classes on students' drug behavior after 1 month, 3 months, 6 months, 9 months, and 1 year after starting the class. So we're looking to see whether or not there's no pre-test in this example. We're looking to see, we give a set of martial arts classes, perhaps it's one intervention, but most likely it's multiple interventions. And then we look at an effect 1 month afterward, 3 months, 6 months, 9 months, and a year afterward, partly to see whether or not there's any consistency or any trends that occur, but also to see whether or not the impact of our experiment is lasting. A couple more just comments on variations, extensions, some ideas that we might see that change. Our factorial designs can have many different independent variables and many different levels. We're going to talk about this again in the upcoming lectures and also when we get into our statistical models. But if you have 3 variables, each with 2 levels, you have a 2 by 2 by 2 factorial design. If you have those same 3 independent variables, but they have various levels, independent variable has 3 levels, independent variable 1 has 3 levels, independent variable 2 has 2 levels, independent variable 3 has 4 levels, then you have a 3 by 2 by 4 design. If you have 2 independent variables, independent variable 1 has 5 levels and independent variable 2 has 4 levels, you have a 5 by 4 design. You can have designs with lots of more independent variables, potentially infinite, but no one would ever do that. There's a lot of problems with interaction effects even when you get up till 4 and 5. And also you can have a lot of different levels. It depends on the type of variable that you're working with. I also want to make note of other variations or extensions you might see. I just used the basic pre-test, post-test design here, but the control, we've been using X's and dashes for a treatment and control, but it's okay if you see X1 and X2. It might be treatment 1 against treatment 2, or they might be calling treatment 1 X1 and control X2. You will see those variants. You might also see someone, as opposed to calling it generically X, for my study, maybe I will call that variable HS for healthy snack, which will be healthy snack treatment 1, apple, healthy snack treatment 2, no snack. And then you might also see things like T's and C's and other variants. Read whatever you're working with should define what those variants are. They should tell you the meaning of the variables and the levels that you're working with. The idea of randomness and representation is really important. We've been discussing this throughout all of our lectures and in this lecture and experimentation, and we're going to discuss it again. So I'm just going to give you the short version now, and we'll get into sampling techniques. We're going to come back to this idea, but just the general idea is that we have random selection. Random selection is a process of selection for your sample from the larger population. So we're selecting a sample from a population, and it should be a random process. Random assignment is different. Random assignment is from their sample. We're taking and assigning individuals to experimental and control groups, multiple experimental conditions or control conditions. So random selection, we select people from the population to be in our sample. Random assignment, we select people in the sample to go to different groups. Sometimes we just see the whole process sort of done all at once and it's blurred, but it's very important when it comes to distinctions between experimental, quasi-experimental, and non-experimental designs. And often we can actually save a whole lot of our internal validity and threats to internal validity, even though we may have issues with intact groups. We'll see later on that random assignment may be helpful for us in those cases. And we'll discuss this more again when we get back into our lecture on sampling techniques. All right, we'll use our example, but follow along very similar to one of our examples for interpretations in our chapter. We have 4 groups. We have a pre-test and a post-test. So we can use our example You can also follow along with some of the examples in your textbook. But in this example, we have 4 groups, each with a different treatment. We have treatment 1, apples. They get a healthy snack of apples. Treatment 2 is chocolate. Treatment 3 is chips, and treatment 4 is the control, no snack at all. So group 1 apples, group 2 chocolate, group 3 chips, and group 4 control. Hopefully by now you're moving along with this, and this is becoming second nature. So we have those 4 groups. We would call this a 4-group pretest, post-test, control group design. This is an extension of our pretest, post-test, a very simple version. And part of it is because we don't want to just test in this example. We want to test the impact of potentially other snacks, like some that are sweet and some that are not necessarily sugary snacks. So we have this design and we come up with some results. First thing we notice is that the outcomes for the pretest, post-test for group 1 are not equal. The pretest, post-test for group 2 are not equal, and the pretest, post-test for group 3 are not equal. That is, O1 does not equal O2. That's the pretest, post-test for group 1. Further, we say that the outcome for group 1 and 2, the O2 and O4, they're equal to each other, but those 2 are not equal to group 6. That means basically that group 1 and 2 outcomes are the same. However, they're not the same as the outcome for group 3, O6. We also notice that all the pretests are the same, and that's also equal to the post-test for our group 4, where they got no snack. So some of the interpretations we draw is that there were certainly some experimental treatment effects here, that the effects for group 1 and group 2 are the same, and they're different from group 3. And also the fact that we can say all the treatment effects are meaningful, or I should say are that there are treatment effects, is because we see the difference initially from our pretest to the post. So this is just an example of how we might start to interpret our results. We're really going to focus on interpretations also when we get into our statistical analysis, because the meaning of not difference or difference here, the difference between 2 groups and saying that there's a difference amongst them, is really a statistical difference that we're going to talk about later on. Let's just try one more iteration of this. Same experiment, 4 groups. We randomly assign people to groups. We have a pretest, we have a post-test. Apples, chocolate, chips, and no snack are our conditions, and our outcome is our math test. We find that all of our pretests, O1, O3, O5, and O7, are equal to each other. We see that O1 is not equal to O2, so the pretest for our apple group is not equal to our post-test. We see that O3 and O4, the chocolate condition, the pretest and post-test are equal. For the chip condition, they're equal. We also now see that O4, O6, and O8, that is chocolate, chips, and no snack, are all equal to each other, but they are not equal to group 1, the apple condition. This would be like if we really wanted to support our hypothesis, we would have an effect of apples. There's a pretest post-test condition difference. There's no other pretest post-test difference. And all of those other outcomes, the chocolate, whether you had chocolate, whether you had chips, and whether you had no snack at all, had no impact. So the only treatment effect here would be due to the healthy snack of apples. And that might be the result we're looking for. So I'll point you back to the book and for some of those examples. There's some useful ones in chapter 7 and even in getting into some of the other chapters. And this is just a start. So this is just the precursor when we start to look and examine results in both descriptive statistics and inferential statistics. If you noticed, I gave you a lot of introductions, and so does the text, introduction to a topic like random sampling or results, and then there'll be, or measurement, and then there's going to be whole chapters on those later on. In my experience, I very rarely get to work with real, true experimental designs. Most of the time, there's this like continuum between non-experimental, quasi-experimental, and true experimental. The reason we just don't start with quasi-experimental is because it's all a continuum anyway about control, whether you have control through random assignment or selection or not. So all of these designs we learned in experimental design are going to be relevant. Their structures are going to be relevant when we move into our next lectures coming up in quasi-experimental design and non-experimental design. So in my experience, most of the time when I'm working with my colleagues, we're doing a lot of experimental design, quasi-experimental design and mixed methods as well. In my personal research, I sometimes encounter an artificial version of those experimental designs when I do simulation work. But we will see that this is a continuum. The type of designs that we're using, the structure of design might stay the same, but it might be impacted on whether or not we could randomly assign or randomly select from the population those people we're interested in working with.